Hi, this is Jack Dongarra from the University of Tennessee. And I'd like to talk about innovation driven by advances in high performance computing. So the first question might be, what is high performance computing? You can think of it as a sophisticated scientific piece of equipment that's used for scientific discovery. Very much like the James Webb telescope is used for astronomy. But in this case, we're going to be using computational science to look at and to do simulations. So HPC involves aggregating the computing power to solve complex problems at high speeds. And the common use cases for simulation are really quite broad. We can think of looking at developing clean energy techniques, maybe through the advancements in combustion engines. Think about having more resilient power grids, looking at climate change and what the effects of those climate changes might be, looking at cures for cancer, looking at advanced materials. All of these things can be modeled and simulated using high performance computing, and those simulations help us drive forward science. So science has been carried out by theory and experimentations for many years. Think about theory as a paper and pencil kind of computation, and experiments is where we actually build the physical experiment to carry out those theories that we have. And theory and experiments go hand in hand in the sense that the experiments may cause changes to the theory, and the theory may cause us to rethink the experiments themselves. So those things have limitations. Sometimes it's too difficult to build a wind tunnel to carry out the experiments, or sometimes things happen too slowly, so we can't really understand what happens to climate modeling or think of two galaxies colliding. We can't wait for that experiment to happen, so we do a simulation instead of that. Or sometimes it's too dangerous to carry out those experiments themselves. And simulation, computational science, is a paradigm which uses high performance computing to simulate these phenomena and using the laws, basic laws of physics and numerical methods to help with those simulations. So why does this matter? Well, we think about using high performance computing because we were able to solve complex problems much faster than we would with traditional methods. HPC systems are designed to solve complex, computationally intensive problems at speeds that far exceed those of traditional computing systems with thousands and maybe millions of processing cores that are working in parallel. So HPC can reduce the time from days to weeks to mere hours or even minutes. We think about scalability. HPC systems can handle massive amounts of data in the computations. One of the key advantages of HPC is its scalability, so we can handle larger and more complex problems as data volumes increase. HPC allows us to carry out things with greater fidelity through the use of higher precision. They allow computational simulation in models. They allow high levels of precision in the simulation, which are essential for many of the computations that are done in science and engineering fields. HPC-driven simulations can model airflows and structural stresses at high precision and reducing the need for physical prototypes and testing. In climate modeling, detailed simulations powered by HPC allow researchers to predict long-term climate patterns with greater accuracy, which is critical for understanding climate warming impacts. And the impacts really apply to many fields: medicine, finance, climate science, and many more. HPC speed, scalability, and precision make for a driving force behind major innovations across numerous fields. We've had an evolution of HPC technologies. I started out by using scalar machines and went to vector computers. The canonical classical vector computer was designed by Seymour Cray. The Cray 1 was an example of that. In the late 70s and early 80s, we saw these computers being used for high performance computing simulations, really driving HPC. Those were replaced by shared memory processors when we had microprocessors becoming much more powerful and much cheaper they replaced those classical vector supercomputings. So we had parallel processing coming into play. Shared memory was used, and that progressed to distributed memory as we had more and more processors, and then we had massively parallel systems in place. At the turn of the century, we saw Linux clusters and more advanced efforts being used. Today, we see this rise of GPU-based computing and cloud-based HPC resources. GPU computing allows for the computational power to be spent in the GPU. GPUs are very powerful at doing numerical computations, not so good at some of the other logistical things that take place in a program, but for numerical computations that are computationally intensive, we're driven towards using GPUs to offload, let's say, the computation to the GPU, allowing the computer to run much faster. And today, we see AI being used in many ways in computational science, being used to help accelerate the speed at which we can solve those problems and look at things more appropriately. And on the horizon, of course, is quantum computing, which has even greater capability potential, although I would say that's many years away. So along the way, we've seen the implementation of these hardware features being augmented with many other properties in the hardware. We have prefetching of instructions, we have pipelining, we have vector instructions, parallel processing, speculative execution of instructions, interleaving of instructions through the execution. We have array languages being developed and various forms of parallel computing that were in place. Here's a typical example of one of high performance computing, how high performance computing is put together today. They start with a commodity processor, and that commodity processor has a number of cores on it. And those cores can share memory. They can exchange information very simply by putting information in memory, and other cores, other processors can extract that information. And we take those chips and put them on a board. So we have a number of these chips, each of those chips having multi-core capability on a computer board. And then we take that board and those chips and we augment them with GPUs. So we think about one of those sockets which have multi-core processors on it being augmented with one or more GPUs to allow it to, again, offload the computation, the computational intense parts of the computation, to allow that aggregate to achieve much higher performance. And then we take those boards and put them into a cabinet. So we have a cabinet, a rack that's filled with these boards, each board made up of multi-core processors plus GPUs to do the computation. And we're not going to be satisfied with just one of these cabinets. We think about aggregating them together and putting them in a room. So think of a room about the size of 2 tennis courts filled with racks of these machines. And that's where we are with our fastest supercomputers today, filling out that kind of ensemble, achieving really high rates of execution. So high performance computing is used to do simulations. They're used to do simulations for climate modeling, combustion, nuclear reactors, stockpiled stewardship, material designs, accelerators, and they're all being driven by HPC, all using advanced mathematical techniques that are trying to model perhaps a 3-dimensional partial differential equation and looking at how that differential equation progresses over time. In high performance computing, the environment that we have today is highly parallel using distributed memory. The programming environment usually has MPI or OpenMP being used in that way. MPI is used between the nodes of the machine, and OpenMP is used within a node of the machine. One of the fastest computers today is a computer at Oak Ridge National Laboratory. It's called Frontier. It's capable of executing at 2 exaflops, and this is full 64-bit precision. So an exaflop is 10 to the 18 operations per second. So that's an incredible amount of computing power that we have. I have a hard time getting my hands around that number exascale, Think of the number of grains of sand. The number of grains of sand on the Earth is about 7.5 exascale grains of sand. So this computer is capable of doing 2 exaflops worth of computing every second. And this machine has around 9 million cores in it. It has 9,408 nodes in this machine. It consumes 30 megawatts of power, and it gets most of its compute power from those GPUs. So 98% of the compute power is coming from the GPUs of that system. These machines are heterogeneous. They have commodity processors together with commodity GPUs that are being used. The communication is one of the most expensive things you can do on this computer. We used to think floating point operations was expensive on computers. Today, floating point has been over-provisioned, I'll say, and communication is really the most expensive part of the computation that we do. And the traditional way of thinking about computing would be if we had 2 algorithms that did roughly the same thing. One algorithm did more floating point operations than another. We would choose the one that had less floating point operations. But today, that's not true because of the computational, because of the cost of doing the communication. So we would choose the one that had less communication if we had a choice between 2 algorithms. And we traditionally think about computations for scientific computing being done with either 64-bit or 32-bit accuracy. And there's a format for that, and computers across all of them use that IEEE format. But today, because of the advent of AI computing, we see that AI doesn't need those full precisions. And we see hardware being produced which has much less precision in the computations available in the computations. So they still retain 64-bit and 32-bit floating point arithmetic, but now we have 16-bit floating point arithmetic, or even 8-bit, or even 4-bit floating point arithmetic. And those lower precisions are there really to do AI computations, to do transformers, or to take a look at the neural networks that are in place on these computers. We need less precision. So HPC is key for industrial applications. It's being used in a number of ways. It's being used in healthcare. HPC has revolutionized the healthcare industry by enabling the analysis of massive biological data sets, such as those used for genome sequencing. It's used for financial risk modeling, real-time trading, fraud detection. In finance, we see HPC systems being used for this real-time risk modeling, enabling financial institutions to analyze vast amounts of data sets and predict the market trends, which are essential for making informed decisions. We see this being used in the energy sector. So the energy sector relies on HPC for tasks such as seismic imaging, which involves analyzing large data sets to map subsurface formations for oil and gas exploration. We see it being used in the automobile and manufacturing areas. HPC is essential in automobile and manufacturing industries for simulating and modeling the product design. And we see it being used in media and entertainment. So media and entertainment use HPC to accelerate the creation of high quality animations and visual effects by reducing the rendering time for complex scenes. So these are just a few ways in which they're having an impact. Another way is with digital twins. So we see that digital twins have a way of representing a physical object in a digital form, and the physical object is used to involves creating this virtual model of the physical object, the systems, and the processes that can be monitored and simulated and optimized in real time. So there's a playback between the digital object and the physical object in this using digital twins to do the modeling, where we examine what happens at a digital level and maybe make changes to the physical object. And that physical object, of course, would be reflected in the changes to the digital object. And these can take place on very small scales or very large scales, where we're doing complex simulations of things like an oil field. So AI is all around us. We use generative AI as just the next step in the process. We use it for speech recognition and understanding. AI-driven speech recognition systems are now an integral part of our daily lives and enable devices to understand and respond to voice commands. Siri, Alexa, Google Assist are just a few examples of that. We have face recognition and gesturing recognition that are being used today on smartphones. We see it being used in airports. We see it being used to allow devices to interpret our movements so they can apply to various features. We have real-time language translation now. Google Translate is an example of that. Microsoft has a version of it that use AI to instantly translate spoken and written languages, making it easier for people to understand and to communicate. And of course, there's things like vehicle avoidance, vehicle collision avoidance, and self-driving, which are all part of the AI use in advanced driver-assisted systems. So we have collision avoidance that uses AI techniques from the sensors in the cameras to detect potential objects that might interfere. AI is really having a tremendous impact across sciences. If you take a look at the publications that are coming out, so this graph here gives a sense of that. So these are various fields, and we're looking at publications in this field and how AI is being used in the publication in the scientific areas. Great increases. So there's great changes as AI is being engaged in various disciplines, and that's being reflected, of course, in publications that appear out of those areas. So in AI, in deep learning, it needs to do numerical computation. It needs small matrix operations. That's sort of a backbone of these neural networks, but they can get by with short precision. So perhaps 16-bit or even 8-bit floating point arithmetic can be used to help carry out these computations and get things going at a much greater level. So HPC is driving innovation in AI and machine learning. HPI has really become a transformative force in AI and machine learning, powering advances that handle massive amounts of data with complex algorithms and unparalleled speeds and efficiency. So these neural networks and reinforced learning models involve millions and billions of calculations that really are requiring the high performance computing to carry them out in a timely way. HPC systems often use GPUs or TPUs, tensor processing units. When you hear the word tensor, think of matrix multiply. These are optimized for processing, and performing these calculations allows the AI models to really analyze and to learn from vast amounts of data very efficiently. So HPC supports mixed computations, which balance the overall speeds of these things. It seems like everybody is making AI chips today. If you look at the traditional manufacturers like Intel, IBM, AMD, and NVIDIA, they're all making chips which fit into the space of AI computations. And that goes also to the hyperscalers, the cloud-based systems. Facebook, Amazon, Google, Apple, Microsoft are all making their own chips. These chips are chips that are used in their cloud services, but they don't sell these chips. They just use them as a service that they can provide manufacturers, they can provide users, and those chips then provide a capable way of doing this. And there's many companies that have sprung up and are helping to provide technology that allows AI and machine learning to take place at a much higher rates of execution than we had before, really driving AI forward in this way. Today we have foundational models that we use for computation. These foundational models allow us to do the analysis. So we have a tremendous amount of data that we're going to feed into these models. They're going to be trained with all the data. Think of scraping all of the data that we have on the internet, the text, the imaging, the speech, the data structures are going to be used in the training process. That training then goes into these foundational models, and the foundational models get refined by adapting them to the specific areas that we're interested in looking at. Perhaps a better way of seeing this is we're going to be taking all of the data, all of the internet basically, and using it for training. We have a model that we have which has a certain number of parameters, say 100 million to 2 trillion parameters in the model. We have all of the data on the internet, 10 to the 12 tokens, 10 to the 9 images that we're going to be using in the training process. The training process is something which is very time consuming, even on the fastest computers we have today. So it's estimated that for some of these models, some of these large language models, think of ChatGPT, it takes perhaps between $10 million and $200 million of GPU time to do the training. And the result of that is a pre-trained model. In some sense, that pre-trained model has the basic education of an undergraduate from a college. And that pre-trained model then goes to the next phase. So the estimated cost of doing that pre-trained model is really growing as times goes by. And we're going to see more and more of that happening. But that pre-trained model then is fine-tuned to look at a specific area. And that fine-tuning uses specialized data along with human input feedback into the model. So that fine-tuning is also very expensive in terms of compute time. It costs around $100,000 to $1 million of computer time to do that fine-tuning. And it requires human impact so that we have this annotation of queries that go into the system, which is used in the process of fine-tuning it. And the result of that is a specialized model. And that specialized model can be for medical advice, education, training, chip design, or what have you. And that specialized model is then used in the inferencing part, the end services, if you will, of a query coming in from a user and answers being given. And this part of the process is very quick. It takes less than a second of GPU time to do this, and it takes quite a small amount of data that goes into the system to extract that information. So that's sort of the process of these large language models. Very expensive, very time consuming, very computationally intensive in the training part and in the fine tuning. And then the final part coming out, of course, is very quick. So there are many challenges in the use of high performance computing. Things such as power and energy consumption is certainly one of them. We think about these computers and the power requirements are just enormous. You know, I mentioned a high performance computer at Oak Ridge National Lab consuming about 20 megawatts of power. In East Tennessee, where that computer is situated, it's about $1 million per megawatt year. So if I use a megawatt over a 1 year period, I'm going to get a bill for $1 million. So $20 million would be the cost of just turning that computer on. So very high in terms of the energy consumption. Data management, of course, is a key issue, the storing and the management of that enormous data sets. There's a high cost associated with the HPC infrastructure. And of course, to maintain that over a period of time is an expensive proposition. We have scalability and integration of AI today with edge computing and cloud-based services all going into that. An example of a system that's just being put in place for AI-based computing is one here in Tennessee, in Memphis. Elon Musk has just put in place 100,000 GPUs that are going to be used in his AI complex. And this 100,000 GPUs is requiring 70 megawatts of power. So there's not enough power in the region to satisfy this need at the moment. So he has brought in 14 massive mobile generators, gas generators, that are being used to power this facility. Each of these trucks is about 2.5 megawatts of power, and that augments the power that can be obtained from the grid and to fuel his AI-based capabilities. So he has 100,000 GPUs in today. It took about 122 days for that installation to take shape, and that's up and running. And he's just ordered another 100,000 GPUs from NVIDIA to build out his total system. Microsoft and OpenAI are planning to put in place a $100 billion supercomputer called Stargate AI. It's 100 times the scale of the current data centers. It has on the order of 10 million GPUs, and it'll require about 5 gigawatts of power. So about the power output of a nuclear reactor will be needed to fuel this ensemble. So the future of HPC will be characterized by advances in performance, hopefully energy efficiency, AI integration, and this hybridization of different computing resources. We think about CPUs and GPUs today. Quantum is something on the horizon, along with basically edge computing to help drive these resources. These developments will enable breakthroughs across various scientific, industrial, and commercial fields, making HPC the central technology in addressing some of the most challenging problems that we face today. So let me conclude by saying the takeaway here is HPC, the hardware that's used is constantly changing. We went from scalar to vector to distributed memory to accelerators. We have the use of mixed precision today with the AI-based approach. Algorithms and software advances usually follow the hardware so that the hardware is put in place, and then we are expected to develop the software and the algorithm infrastructure to use that hardware. And that results in a lot of inefficiencies in terms of effectively using the hardware. So there's plenty of room at the top. There was an interesting paper that was produced a couple of years ago by Charles Leiserson in Science. And the title of the paper was, "There's plenty of room at the top. What will drive computer performance after Moore's Law?" And that's a riff, of course, on Feynman's classic lecture about quantum computing back in 1959, where the title was, "There's plenty of room at the bottom." Thank you very much for your attention. I'm sorry I can't be there. I wish you a successful conference.